In this video we're going to build on what we've learnt in previous videos and discover how we can find the equation of a straight line in the form y is equal to mx plus c when all we're given are the coordinates of 2 points that that line passes through. Now it's far more likely when we're solving problems that we're going to know 2 points that a line passes through than we would know the equation of that line. But often, in order to solve the problem mathematically, as we're going to see later on, we're going to need the equation of the line. Thus, what we're looking at in this video can be used in exactly those scenarios. It can allow us to take those 2 points, use their coordinates to find the equation of the line, which would then allow us to solve the problem using the equation of the line. So let's say we've been given 2 points, and let's say, just for example, that we're given the points 2, 2 and 6, 4. So 2, 2 and 6, 4. We know that those 2 points, and I should probably label them with their coordinates, so 2, 2, 6, 4, there we go. We know that these 2 points are going to define a single straight line. There is only one straight line that will pass through these 2 points. And we can draw that now. Now we know, of course, that this straight line does extend infinitely in both directions. So I'm just going to draw part of the line here on the whiteboard. But we know that 2 points will define a straight line. As I said a second ago, there's only one straight line that will pass through those 2 points. We saw in an earlier video when we discussed the line equation here that there are 2 properties that we can manipulate, the gradient of the line and the intercept of a line, and that those 2 properties also define a specific line. Therefore, given that we know that any 2 points will define a specific line, and given that we know that the gradient and intercept will also define a specific line, we should be able to derive a mapping that converts the coordinates of those 2 points into values of the gradient and the intercept for the line defined by those 2 points. Now we're going to deal with the gradient first, and then we're going to look at how we can calculate the intercept. And as we saw in the earlier video, the gradient defines the relationship between movement in x and movement in y. The gradient value m tells us that for every single unit we move in x, it tells us how many units we move in y. Now the gradient is constant over our entire straight line, which means we can take any 2 samples on this line and work out the gradient from it. And since we're given those 2 samples, we're given those 2 points, it should be fairly easy to calculate the gradient using their coordinates. So what do we need to know? Well, we eventually need to know how many units do we move in y for a single unit of movement in x. But what we can first calculate is how many units have I moved in x between these 2 points, and how many units have I moved in y between these 2 points. So how are we going to do that? Well, firstly, how many units have we moved in x? To calculate this, let's take the second point's x-coordinate, which is 6, and subtract from that the first point's x-coordinate, which is 2. That's going to tell us the distance in x between these 2 points, which we know is 4. And we can see that here on our line drawing. We can see that indeed if we start at 2, we move 4 units over, we get to 6. So we can see that this is indeed the correct calculation. And we can apply this exact same approach, if you will, to calculate the change in y. So again, we take our second point's y-coordinate. We subtract from that the first point's y-coordinate, and that tells us how far we've moved in y. We started at 2, we've moved up to 4, therefore we've moved 2 units in y. So right, we know we've moved 4 units in x, and over those 4 units, we've moved 2 units in y. But we want to know how many units we move in y if we move a single unit in x. So how are we going to work this out? Well, what if we were to divide both values by 4? If we were to divide our movement in x by 4, 4 over 4 becomes 1. That means we have moved 1 unit in x. That's exactly why I chose to divide by 4. I want to divide by how far we've moved in x, so our movement in x becomes 1. If we were to do the same with y, 2 divided by 4 becomes a half. So what we've done is we've taken the change in x and the change in y, and we've scaled this down so that we've only moved 1 unit in x and worked out how far we would have moved in y. So for a movement of 1 unit in x, we move a half unit in y. And that tells us that the gradient of this line, our m value for this line, is a half. Now it's important to note that it does not matter which order those points come in, as long as we take the coordinates of one point and subtract the coordinates of the other point from that. And we can see this if we were to switch the 2 points over. So originally I said this is our second point and this is our first, and I subtracted the coordinates of this point from the coordinates of our point 6, 4. If I was to switch that around, you'd notice I take 2 and subtract 6 from it. 2 minus 6 is equal to minus 4. I take 2 and subtract 4 from it. 2 minus 4 is equal to minus 2. If I divide the change in y by the change in x, minus 2 divided by minus 4, these two negatives cancel and they give us the exact same value. So as long as we're subtracting the coordinates of one point from the coordinates of another point, we're going to get the correct value. So now that we've seen how we can calculate the gradient using numbers from our example, let's write a generic formula for calculating the gradient that uses simply variables and constant values to represent the coordinates of our points. So I'm going to make some room for ourselves really quick. So whereas in our example we said we had the point 2, 2 and the point 6, 4, what I'm going to do is say in our generic case, we have 2 points. The first of those points is going to be the point x1, y1, and the second of those points is going to be the point x2, y2. And how do we calculate our gradient? How do we calculate the value for m? Well, we've seen that m is equal to the distance travelled in y divided by the distance travelled in x. So m is equal to the distance travelled in y. Well, we know if we take one of our y coordinates and subtract the other y coordinate from it, it will tell us the distance travelled in y. So if we were to take y2 minus y1, that tells us how far we've travelled in y. And how far have we travelled in x? That's going to be x2 minus x1. So we take the distance travelled in y, we divide that by the distance travelled in x. The only important thing to note here is that we must make sure we take one of our points and subtract the other point from it. Therefore, it's either y2 minus y1 over x2 minus x1, or y1 minus y2 over x1 minus x2. We must have both either y2 and x2 on the left, or y1 and x2, or sorry, y1 and x1, and then y1 and x1 over here on the right, or y2 and x2. We mustn't switch these numbers over because we must take one of our points and subtract the other point from it. But we can see now, given any 2 points, we can calculate the gradient very easily. So that gives us the generic formula for calculating the gradient of a line given 2 points. But how do we calculate our intercept, our c value? Well, let's go back up to our numeric example before we look at the generic example. And we calculated here that m was equal to 4 over 2, equal to a half. And we know, therefore, that our line equation is going to be y is equal to a half x plus c. We can take one of our points, one of the points that we know is on the line, and we can put the information of that point into our equation to work out the value of c, because we know a value for y and a value for x that satisfy this equation that allows us to work out the value of c. So let's take the point 6, 4, for example. If we were to put that into the equation, I'm going to need some space to work. So I think the best bet is going to be to bring up a new layer and hide out all of these guys. Fantastic. So we saw that y is equal to a half x plus c, and we saw we had 2 points on the line. We had the point 6, 4, and we had the point 2, 2. If I was to take one of these points and put that into the equation, well, we can see y is equal to a value of 4. So 4 is equal to a half. X is equal to the value of 6. So 4 is equal to a half of 6 plus c. So 4 is equal to 3 plus c. If we rearrange this to find c, I'm going to subtract 3 from both sides of the equation. 4 minus 3 is equal to c. 1 is equal to c. Therefore, c is equal to 1. So our intercept value is equal to 1. And we can double check this by using the other point's coordinates in the exact same manner. So in this case, 2 is equal to a half of 2 plus c. So 2 is equal to 1 plus c. Rearranging this, 2 minus 1 is equal to c. Therefore, 1 equal to c. c is equal to 1. So by using one of our points that we know lies on the line, we can substitute its coordinate values into our equation, and we can use that to determine the value of c. So that's what we can do graphically when we have, or rather that's what we can do when we have numbers using a true example. And we can check this. If I was to bring back our previous workings, we can see that indeed our intercept here is 1. We are indeed cutting the y-axis at 1. This is all very well when we're working on paper and we have numbers that we can put into our equation, but we need a generic version. So let me bring back up this layer. Fantastic. And scroll down. So we know that the coordinates of one of our points, we want to substitute that into the equation. Well, we can pick either of the 2 points, and I'm going to pick the point x1, y1. We know that that is the coordinates of one of our generic points. And we need to put this into our equation. So we've seen our equation is y is equal to mx plus c. So we can say that y1 is equal to mx1 plus c. And we can now rearrange this. So if we were to say y1 minus mx1 is equal to c, therefore c is equal to y1 minus mx1. So if c is equal to y1 minus mx1, we can now substitute that back into our generic equation. If this is what c is equal to, then we can substitute that back in here. So y is equal to mx plus c, therefore y is equal to mx plus y1 minus mx1. Notice what we've got here. M is a gradient, we know how to calculate that. y1 is a constant value, it's the coordinate, the y coordinate of one of our points. x1 is a constant value, it's the x coordinate of one of our points. M again is our gradient, and then we've got our x variable here and our y variable here, which are the 2 variables of our equation. So don't confuse y and x, which are our variables, with y1 and x1, which are coordinates of points on our line. So now that we've got this, let's start rearranging things slightly and using some of our algebraic laws to simplify this equation and get the final form of the equation. So let's rearrange this just so that things are a little more clear for the next step. So y is equal to mx minus mx1 plus y1. So I've simply just changed the order of that equation. And now we can use our distributive law to say that y is equal to mx minus x1 plus y1. So I've simply taken m and factorized using m so that we get mx minus mx1, which we have up here. And now that we have this, we know the value of m. We saw on an earlier slide, I believe, we saw that our value of m, I can just write this out again, m is equal to y2 minus y1 over x2 minus x1. We've seen that, so we can now substitute that into our equation. And that gives us the final generic equation that says that y is equal to y2 minus y1 over x2 minus x1 times x minus x1 plus y1. And there is our equation. So if we are given 2 points x1, y1, x2, y2, we can now substitute the coordinates of the points into this equation. Everything will eventually be able to be calculated. We can calculate our gradient. We can then expand everything. We can see how we could calculate our c-intercept value if we wanted, once we know our gradient and we know our points. Or if we simply wanted an entire equation that we plug numbers into, then we could evaluate this equation, because this is equal to mx plus c. We know that y equals mx plus c, therefore if y is equal to this, then they're equal to the same thing. Thus, in most cases where we are solving problems using an equation, generally all we need to know is some value for this. So if we're given 2 points and we need to determine a line equation using those points, we can simply plug the values of those points into this equation. So we can test this. We can test this using the points that we've been given in our earlier example, 2, 2 and 6, 4. And let's make sure that we get the same answer. So just to verify, as I scroll back up, we saw in the end that our intercept value was c. As I find a layer I can draw on, there we go. So we saw that our intercept value c was a value of 1. That meant our final equation was y equals a half x plus 1. So this is what we're expecting to get. Let's check that by using our 2 points into that equation. So I'm going to hide all of these guys out, bring back our layer that we've been working on, and let's plug our values into the equation. So we know that x1, y1 is equal to, and again we can choose either point to be x1, y1 or x2, y2. It doesn't matter as long as one point is x1, y1 and the other point is x2, y2. So I'm going to just say that 2, 2 is x1, y1. x2, y2 is, I believe it was 6, 4. There we go. If we now plug these into our equation, let's make sure that we get the same result. So y is equal to y2, which is 4, minus y1, which is 2, over x2, which is 6, minus x1, which is 2, multiplied by our x variable minus x1, which is 2, plus y1, which is 2. If we now expand that out, y is equal to 4 minus 2 is 2, over 6 minus 2 is 4, multiplied by x minus 2 plus 2. And I have actually run out of whiteboard space, but what I'm going to do is rather sneakily slide this up. I'm just sliding the layer up, so it's going to go off the top, but that doesn't matter. So I can keep working. So y is equal to 2 over 4 x minus 2 plus 2. If we continue expanding that, that means that y is equal to a half. I'm going to then multiply out this bracket, so a half x minus a half times 2, so minus a half times 2 plus 2. That means that y is equal to a half x minus 1 plus 2, which means y is equal to a half x plus 1. The exact same equation that we saw, as I hide this and bring everything else back. The exact same equation that we saw up here. So indeed, it does work. Fantastic. So before I wrap up this video with a few questions, there's something else I'd like to point out. Now, as mathematicians working on paper, this equation serves as well. However, if we were to program our equation, which I guess it would be useful if I pointed to the equation I'm referring to. So this equation right here, our equation of the line given 2 points. If we were to work this on paper, absolutely fine. But if we were to program this equation, we need to be careful of a special case. In the previous video, we saw there are two special cases with our lines, where the line is perfectly vertical and where the line is perfectly horizontal. So let's look at those two cases and see how that affects our equation. So in the case that our line is perfectly horizontal, well, let's write out our equation again. That's y is equal to y2 minus y1 over x2 minus x1 times x minus x1 plus y1. Fantastic. So when our line is perfectly horizontal, that means that y2 is going to equal y1. We know that with a horizontal line, 2 points on that line, the x-coordinate's going to change, but there's no variation in y, so y2 is equal to y1. So what happens to our equation in that case? Well, this part of the equation, our y2 minus y1, is going to equal 0 because we've got one value and we're taking the same value away from it. So our equation becomes y is equal to 0 over x2 minus x1 x minus x1 plus y1. Well, 0 divided by anything is 0, so this whole part becomes 0. 0 multiplied by anything becomes 0, so this entire part of the equation becomes 0, leaving us simply with y is equal to y1. So we do indeed get the correct result when we have a horizontal line. We still get y equal to some constant value. However, our other special case, where the line is perfectly vertical, we do need to be careful, because in that case, and I'm going to actually erase this so that I can work underneath our equation again. So in the case that everything is vertical, we know that x1 and x2 are going to be equal to each other, just as the same as when it was horizontal, there's no change in y, so all the y coordinates are equal. When it's vertical, there's no change in x, all of our x coordinates are equal. So that means that x1 is equal to x2. Well, in this case, let's see what happens to our equation. So we have y is equal to y2 minus y1 divided by, well, if x2 is equal to x1, that means that when we subtract x1 from x2, we're going to get 0. So hopefully all of the programmers out there are now going to be screaming with what's wrong with that equation. I'm going to finish it off. It's going to be x minus x1 plus y1, but hopefully any programmers are now screaming at me, telling me what's wrong with that equation. You guessed it. We're dividing by 0. So in the event that the line is perfectly vertical, if we try to evaluate our equation by plugging the numbers in, we're going to get a divide by 0, which is going to make our program explode, which is not at all good. So we do need to be aware of this when we're writing a program, and we need to make sure that we perform a check in that program to see, does x2 equal x1? Because if they are equal, then we know we have a vertical line, and our equation needs to become x is equal to x1, as opposed to using this equation here. If we use this equation to work out the equation of our line, we're going to get a divide by 0, and it's going to explode. So you do need to be careful with that if you are programming in this particular equation. Alright, so now that we've seen our equation, let's test it out. So I'm going to set a handful of questions for you. I'm going to give you the coordinates of 2 points, and in each example I'd like you to work out the equation of the line that passes through those 2 points. So that's simple enough. So let's bring up a new whiteboard. There we go. And let's set question 1. So question 1, we're going to have the point 1, 5 and the point 3, 7. So they're the 2 points that our line passes through. I want you to go ahead and pause the video and calculate the equation of the line that passes through those 2 points. Once you've found the equation, or if you get stuck, unpause the video. I'm going to work through the answer. Okay, welcome back. So we know our equation, our generic equation, is y is equal to y2 minus y1 all over x2 minus x1, x minus x1 plus y1. So let's just simply plug numbers into that equation. Now, again, doesn't matter which of these points we take as x1, y1, and which we take as x2, y2. I'm going to take 1, 5 as x1, y1, 3, 7 as x2, y2. Don't worry if you chose them the other way round. So long as you get the same final answer, then that's absolutely fine. So y is equal to y2, 7, minus y1, which is 5, divided by x2, 3, minus x1, which is 1. X minus x1, we saw that's 1, plus y1. y1 is 5. Scroll down. So if we start simplifying this down, that means y is equal to, well, 7 minus 5 is 2, 3 minus 1 is 2, x minus 1 plus 5. So y is equal to 1. X minus 1 plus 5. Therefore, y is equal to, well, the 1 doesn't really affect anything, but we'd have 1 times x, which is x, minus 1 times 1, which is minus 1, plus 5. So y is equal to x plus 4. And that is the equation of our line that passes through the points 1, 5 and 3, 7. So hopefully you got that answer. If you didn't get that answer, the first thing to check, did you use the correct equation? Did you use this equation here, our generic equation? If you did, then just make sure that you carefully work through that all of your various calculations were evaluated correctly when you expanded this parentheses, the multiplication, that expanded correctly, and that all of your various calculations were indeed accurate. Because it's simple to make, little mistakes with multiplications or additions and subtractions. Everyone does it. Everyone makes mistakes, especially if you're working through things quickly. And just one mistake at any point in the workings will, of course, throw off your final results. If you didn't get the exact same result, don't worry. Just check your answer. Make sure you're using the right equation. And if you're using the right equation, make sure that you work through everything correctly. So that's question 1. I'd now like to set another question. So let's bring up a new layer. And for question 2, I'd like you to find the equation of the line that passes through the points 4, 2 and 2, negative 6. So go ahead and pause the video, and then when we come back, I'm going to work through the answer. Alright, welcome back. So it's the exact same equation. It's y is equal to y2 minus y1 over x2 minus x1, x minus x1 plus y1. And we're going to simply plug numbers into that equation. Now I'm going to take 4, 2 as x1, y1. That's just an arbitrary decision, but y is equal to, so y2 is negative 6. Minus y1 is 2, divided by x2 is 2, minus x1 is 4, x minus x1 is 4, plus y1 is 2. And now let's expand that. So y is equal to minus 2, minus 6 minus 2 is minus 8, over 2 minus 4 is minus 2, times x minus 4 plus 2. So minus 8 divided by minus 2 is 4, x minus 4 plus 2. Therefore, y is equal to 4 times x. 4 times minus 4 is minus 16 plus 2, which gives us the final equation of y is equal to 4x minus 14. So hopefully you got the same answer as me. I'd like us to work through just one last question. It's going to be a little trickier just because I'm going to throw in negative numbers in the coordinates, a lot of negative numbers, but as long as you work through everything nice and slowly, you shouldn't have any issues. So let's bring up a new layer and let's set question 3. And question 3 is going to ask you to find the equation of the line that passes through the points minus 3, minus 2, and minus 2, minus 3. So go ahead and pause the video. When you come back, we're going to work through the solution to this final question. Okay, welcome back. So we've seen again many times now that our equation is y is equal to y2 minus y1 over x2 minus x1 multiplied by x minus x1 plus y1. And I'm, again, as an arbitrary decision, going to take the point minus 3, minus 2 as our point x1, y1. So let's plug in those numbers. Y is equal to y2 is minus 3, minus 3, minus y1 is minus 2. So I'm going to write this in like so, and then I'll come back and simplify everything later. x2 is minus 2, minus x1, which is minus 3, multiplied by x minus x1 we saw is minus 3, plus y1 we saw is minus 3. Okay. Sorry, y1 is not minus 3, that's y2. y1 is actually minus 2. Okay, so there are our numbers. Let's simplify these. Where we have two negatives, that needs to become a positive, so that'll be the first step. So y is equal to minus 3 plus 2 over minus 2 plus 3, x plus 3 minus 2. We can now calculate this. So y is equal to, well, minus 3 plus 2 is minus 1. Minus 2 plus 3 is 1. X plus 3 minus 2. Negative 1 divided by 1 is negative 1. X plus 3 minus 2. We can expand the bracket now. So y is equal to minus 1 times x is minus x. Minus 1 times 3 is minus 3. Minus 2, giving us the final result of y is equal to minus x minus 5. Okay, so to recap, we saw that any 2 points will define a straight line, and we saw that using the coordinates of those 2 points, we can calculate the gradient of the line m and the intercept c. And we saw, as I hunt down somewhere in here, maybe this guy? Nope. This is probably on one of these layers. Here is how we calculate m using those points. We also saw how we calculate, I believe that's on here. As I try and move everything, please bear with me. Here we go, buried in there. So we also saw how we can calculate c using those points. We then saw how we can combine all of this to calculate the entire equation of a line, right here, using all of that information together. And we saw this both using numerical examples as well as how we can derive this generic solution giving any 2 points, which will allow us using either this or using values for m and c, using our other two equations, to program a solution for finding the equation of the line. And being able to find the equation of a line passing through 2 points can be incredibly useful for us for a number of different applications. As I mentioned earlier, it's going to be far more likely that we know 2 points that the line passes through than that we know the equation of the line. But we're going to see that to solve a lot of problems mathematically, we actually need to know the equation of the line. Thus, what we've looked at in this video can be applied in precisely those scenarios. It can be applied to allow us, given those points, to find the equation. Once we have the equation, we can then solve problems. This is all geared to, well, what if we don't have a specific line, but we want to write some generic algorithm for solving problems? These are the kind of equations that we're going to need. So hopefully everything in this video made sense. I hope you followed along with it well. And with that, that is going to conclude this video. Thanks a lot for listening, everyone.